So I wanted to make this video to talk about a couple of different methods for getting power out of a small off-grid solar system. So this would be a pretty standard setup. I've got a 12-volt lead-acid battery here, a solar charge controller, and then I have a light here plugged into the DC load or the light output, and then I have a wire here that would be plugged into my solar panels. I don't have any panels here, I'm inside. During the day, I'd be getting power in from the solar panels. That would come in here on the PV input and charge the battery, and then these controllers have typically a light or a DC load output, and you can control that by this switch here. Usually it's the right switch on one of these 4-switch units, and there you see the light turned on. You've got an indicator here showing the lights on. I can turn it off. So a little bit of background. I think this basic charge controller design was originally intended for use for overnight lighting, like if you had a security light or a floodlight in a parking lot or something like that. You would take one of these units and hook up a small battery, and you would hook up a solar panel, and during the day the solar panel would charge the battery, and then at night your light would turn on. And a lot of these units inside, if they have a DC load programming option, you'll notice a lot of the options are usually like a number setting. And then they usually have a manual on-off setting like that. So anyway, this DC load output is one option to get power out of your off-grid solar setup. And this has a couple of advantages. One is you get a free light switch, turn the light or your load on and off, and you also pick up the low voltage protection for your battery. I forget what this one is set up for. You could go into the settings, and there's a voltage setting in here that says if the battery gets down to 11 volts, turn this off to avoid over discharging your battery. The other advantage is this typically has some sort of overcurrent protection. If your load goes above that, it'll shut off to again protect the battery from over discharging, if you get a short circuit here. So that current limit is typically not related to the charge controller rating. They're 20 amp maximum charger current and 20 amp maximum load current. But you could get a 30 or a 40 amp charge controller, and they're usually limited to the same 20 amps. 20 amps times 12 volts is about 240 watts. That would be the most power you could extract from this port on a 12 volt system. That would double on a 24 volt system. You are limited in how much power you can get out, and you won't damage the unit. It'll just shut off, and then you'll have to turn the load down and then turn the output back on, and it'll come back on. And then some of these units, I know the EpEver, EpSolar, the tracer charge controllers will actually keep track of amp hours or watt hours of energy that goes out of this port. Say you're running a 12 volt fridge and you want to track how much energy that refrigerator is using. This would be a good way to do it. So those are all advantages of this output. Like I said, the big disadvantage is the power limit. 20 amps is 20 amps. That's the most you can get out of here. Back to the lighting example, using this for overnight lighting, this DC load output has basically nothing to do with the solar panel input. Like right now, I'm getting nothing in on the solar panel, yet I can turn the light on and I'm pulling power. You can see now the battery voltage has dropped Now if I turn that off, this will probably, jump back up to 12.6 volts. So as an example, you might be running like a motor. So here I've got a blower here, a blower motor. So that blower motor might take 200 watts to run, and I might only have a 100-watt solar panel here. During the day, I would be getting 100 watts coming in here, charging the battery, and anytime I turned on that blower, it would pull 200 watts. You can pull more power out of this load than is coming in on the solar panels. What's coming out here is whatever the load needs, and what's coming in here is whatever your solar panels can provide. And if they happen to equal, then the current goes from here over to here. If there's more power coming in, most of it gets dumped into the battery, and then the load just takes whatever's left. But if less power is coming in than your load takes, then power is flowing out of the battery into the load. That's one way to get power out of your unit. The other way, like if you had an AC power inverter, this output here, like I said, is only 20 amps. That's only going to get you maybe 200, 250 watts max on a 12-volt system. So if your power inverter takes more than 20 amps, you're going to want to hook the inverter directly to your battery terminals. And typically that's okay because your power inverter will have some sort of low voltage cutoff and over current protection built into it. So that's another way to get power out. If you need to run like a 600-watt inverter, you would come off the battery, or you can use this if you had an inverter and you also wanted to have a light. You could turn the light on like that, and then separately have your AC power inverter running off the battery. Now a third way you could use this is a 12-volt headlight relay. It can switch, I think, 30 amps. So what you could do is wire the DC load to the coil on the relay. Okay, so I wanted to show you this alternate wiring setup or power setup to operate a DC load using the DC load output, but not being limited to the 20 amp or whatever the maximum output current is here. So what I've done is I've added a 30 amp relay here off of the DC load output. I come over here to this wire, and that goes into a pair of connectors here, and from that I run over here and feed power into that relay coil. So when I turn on the DC load here, that relay coil is going to turn on. That battery positive comes over here to the main terminal on the relay here down at the bottom, and then off of the normally open contact I come out with this black wire, and that comes over to this terminal. So this is actually a switched 12-volt wire here. Kind of hard to see there, but I've got the positive for the light plugged in there, and then the negative I just have wired into the negative of the load. The load negative, the battery negative, and the solar panel negative are all common on this controller. Some controllers are all positive common, but this one is negative common. So just to save running an extra wire from here over to here, I just leave it connected in there. I'll turn on the load here, or turn on this light. So I'll click that, and then the relay clicks, and the light comes on. So now I'm powering the light from this wire. So the battery is supplying current to this relay. It's coming out the relay, going over to here, through the positive into the light, and then back to the negative. So that's the circuit there. But I'm not pulling the light current through here. I'm only pulling the relay coil. You heard the relay click, and then the light goes out. That's just an alternate way to hook things up. So the advantage here is that if you have a high power load, you could run that through this relay, and if the battery voltage got too low, the charge controller would shut the power off here, it would cause the relay to turn off, which would turn off the light or your load, but you're not running all the load power through this 20 amp circuit here. Now the downside of that is that you're using maybe 80 or 100 milliamps of current to turn this relay on. So whenever the relay's on, it's pulling some power out of your charge controller. So yeah, I brought my phone over. It's got the Bluetooth app for this particular charge controller. Got your battery voltage, 12.6. You got 12.6 up there, 12.6 here. This app or controller actually has two separate switches here. One is you can turn the short circuit or overload protection on and off, and then you can come in here and turn the DC load on, and the light turns on there. We get 1 watt of power, 0.1 amps, and that 0.1 amps is to run the relay here. So that 100 milliamps is powering the relay, but the load here doesn't show because I'm taking the current for the load directly off the battery. So the charge controller doesn't know anything about this light. That would be another advantage of using the DC load output, as I now have a Bluetooth enabled 12 volt LED off my charge controller. Yeah, so basically the three ways of getting power out: you can come directly off the battery, like if you were running a large AC power inverter. You can also come off of the DC load output here, and you're limited to whatever current rating your charge controller has. 20 amps is pretty common, but I've seen some of the new EpEver models. They actually increase what they call the discharge rating of their controllers. So their 20 amp controller, 20 amp charging, also has 20 amp discharging or DC load output, but their 30 amp charging has 30 amp load output. The 40 amp charging has 40 amp discharge capability. So this one actually has a fairly decent label. They actually give you all of the important specifications. Other models, you might find this in a user's manual, typically in the back of the manual under specifications. Yeah, if you have any questions about that, post up in the comment section below. And as always, thanks for watching.